at the other end. Another bracket is attached to the shaft of the fixed component. At the other end of this bracket are two areas called targets. As you can see, the stems of the dial indicators are touching the targets. This target will represent the rim of the fixed component's hub. The dial indicator that contacts it will be used to measure parallel misalignment, so we'll refer to it as the P dial indicator. The other target will represent the face of the fixed component's hub. The dial indicator that contacts it will be used to measure angular misalignment, so we'll refer to it as the A dial indicator. In a moment, we'll see how the P and A dial indicators are used to measure the amount of misalignment that is present in both the vertical and the horizontal planes. Now, one thing we'll have to do before measuring misalignment involves determining the amount of deflection in the brackets. Chances are that any dial indicator bracket used for alignment purposes will flex or deflect some small amount while you're using it. In order to obtain accurate dial indicator readings, this deflection, or sag as it's called, must be measured and taken into account when performing an alignment. Some brackets have this information stamped on the bracket. However, if the amount of bar sag isn't known, it will have to be measured before performing the alignment. To do this, the dial indicators and brackets will have to be mounted on a test fixture. But first, you should take a couple of measurements so that brackets can be mounted on the test fixture exactly like they are on the shafts. While the brackets are in place, a tape measure is used to determine the height of the target bracket and the distance between both brackets. Then the measurements are written down. It's also a good idea to mark the shafts along the edges of each bracket so they can be reinstalled in the same place once the amount of bar sag has been determined. The test fixture for measuring bar sag can be an old shaft, a piece of pipe, or a piece of round stock. However, it should be large enough in diameter to prevent flexing that could cause erroneous sag measurements. Here, the dial indicators and brackets have been attached to the fixture, making sure the height and distance between the brackets are the same as they were when mounted on the shafts. With the dial indicators at the 12 o'clock position, the P indicator is adjusted to a 0 reading. It's not necessary to take sag readings on the A dial indicator. The reasons for this are detailed in your text. Now the fixture is rotated to the 6 o'clock position and a reading is taken on the P dial indicator. This reading indicates twice the actual bar sag. The reason for this is that the bar was actually deflected when we had it in the 12 o'clock position. But since we zeroed the dial indicator at that position, we actually negated the sag that was present. So we'll divide the reading by 2 to determine the actual amount of bar sag. In this example, the bar sag is 2 mils. Now, since we'll need to take the amount of bar sag into account when performing the alignment, this value will have to be recorded. Generally, a form called a data sheet is used during alignments to record measurements and other information. This is one example of a data sheet that can be used for the rim and face alignment method. It may not look exactly like the ones used by your company, but chances are it includes similar information. Here, there's space for the equipment's identification, its operating speed, the date, the type of coupling involved, the coupling gap, and the alignment tolerance for both angular and parallel misalignment. We'll be discussing alignment tolerance in more detail later. Here's a space for the bar sag to be entered, so we'll add it. The rest of the form is for dial indicator readings and other measurements that will be discussed as we get further into the alignment procedure. Now the brackets and dial indicators can be reinstalled on the shafts of the equipment to be aligned. You'll need to make sure that they're reinstalled in the same positions. The marks that we made earlier will make that easier. The last thing that needs to be done is to mark the 12, 3, 6, and 9 o'clock positions on the fixed component. These marks will be used to position the dial indicators for taking readings. At this point, we are ready to continue the alignment procedure. Before we go on, though, take some time to review the material that we've just covered in your text. In the last part of the program, we introduced the rim and face alignment method. We saw how bar sag is measured and what a typical data sheet looks like for this method of shaft alignment. In this part of the program, we'll see what's involved in using the rim and face method to measure misalignment in the vertical plane. Measuring misalignment involves taking readings from the dial indicators. Before taking dial indicator readings, though, we'll have to determine certain distances with a tape measure. These measurements are necessary to convert the angular misalignment readings into the actual distance the movable component must be moved to align the shafts. As we take these measurements, we'll record them on the data sheet. Although it's difficult to obtain extremely accurate measurements with a tape, it's usually possible to measure these distances to within 1/8 of an inch. The first tape measurement we'll take is the distance between the center line of the pump shaft and the center line of the A dial indicator's stem. What we need to determine is the swing diameter of the A dial indicator stem. That is, the diameter of the circle through which the A dial indicator travels as we rotate it. So we'll multiply the measurement by 2 and record this value on the data sheet. This value goes here and is labeled D. The next tape measurement we'll take is the distance from the target of the A dial indicator to the center line of the support bolt for the motor foot nearest the hub. This foot is generally referred to as the near foot or inboard foot. As you can see, the dial indicators and brackets have been rotated to about the 6 o'clock position to make it easier to obtain this measurement. Again, we'll record this measurement on the data sheet. It goes here and is labeled X. The final tape measurement is the distance from the target of the A dial indicator to the center line of the support bolt for the motor foot farthest from the hub. This foot is generally referred to as the far foot or outboard foot. This measurement also gets recorded on the data sheet here and is labeled Y. At this point, we're ready to take dial indicator readings. So let's take a moment to establish the proper orientation and then start taking readings. The proper orientation is with the fixed component on the left and the movable component on the right. And if we superimpose a clock face around the fixed component's hub, the 12 o'clock position is on top, 3 o'clock is on the right, 6 o'clock is on the bottom, and 9 o'clock is on the left. Since the brackets are set up in this manner, we'll be using the fixed component's shaft as the reference point. We'll be measuring how much the movable component's shaft is misaligned from this reference point. Since we'll only be measuring misalignment in the vertical plane for now, we'll rotate both shafts so that the brackets are at the 12 o'clock position. We'll use the marks on the pump to make sure we're at exactly 12 o'clock. Next, the face of each dial indicator is rotated so that a reading of 0 is obtained. Now we'll rotate both shafts 1 complete revolution and back to the 12 o'clock position. And we'll need to check the mark on the pump to make sure we're back at exactly 12 o'clock. Then we'll check the dial indicator readings. Both should read exactly 0. The purpose of this step is to make sure that the brackets and dial indicators are securely fastened. If we'd gotten a reading of anything but 0 on either dial indicator, it would have let us know that something had slipped. Since the dial indicators read 0, we can continue. Now, while watching the dial indicators carefully, we'll rotate both shafts until the brackets are at exactly 6 o'clock. In this position, the P dial indicator reads minus 17 mils, and the A dial indicator reads plus 6 mils. We'll need to record these values on the data sheet. As you can see, there are 2 circles here for the initial dial indicator readings. The circle on the left is labeled P. It's for the P dial indicator reading, or parallel misalignment. The box at the top has a 0 written in that represents the 0 reading we set at 12 o'clock. And at the bottom is a box for the 6 o'clock P dial indicator reading. The small area at the left of the box is for the plus or minus sign. So our reading of minus 17 mils would be entered here. The circle on the right is for the A dial indicator reading, or angular misalignment. As before, the 12 o'clock reading has been entered as a 0, and our 6 o'clock reading of plus 6 mils would be entered here. Now, at this point, we've obtained dial indicator readings that can be used to determine parallel and angular misalignment in the vertical plane. However, we'll have to take another set of readings and compare them to the first set. If the readings are the same, we can be certain that we have an accurate set of readings. However, if one or more readings don't match, it indicates that something has slipped, and it'll be necessary to make adjustments and recheck the readings. It's extremely important that any measurement taken when performing a shaft alignment is repeatable. In other words, when you check a measurement for the second time, you should get the same results as the first time. Without repeatable readings, you'll have a difficult time performing an accurate alignment. To complete the alignment procedure for the vertical plane, we'll have to convert our measurements to determine how much the motor must be moved to bring the shafts into alignment. Then we can make the proper moves. And we'll see how that's done in the next part of the program. In the last part of the program, we began discussing the rim and face method of aligning shafts. We'd completed the procedure up to the point where a data sheet had been filled in with dial indicator readings for the vertical plane. The information we obtained tells us the amount of misalignment that is present between the two shafts in the vertical plane. But we still need to determine how this information relates to the actual movement that is required to correct the misalignment. There are a couple of ways to do this, by using formulas or graphs. The use of formulas is covered in your text. In this part of the program, we'll concentrate on how to use graphs to convert the measurements recorded on the data sheet into information that tells us exactly which direction and how much to move the motor in order to correct for misalignment in the vertical plane. Then we'll look at how the actual move is made. The data sheet shows that for this particular situation, the thermal growth characteristics for the fixed and movable components are the same, so we won't have to be concerned with thermal growth in this example. The first thing we need to do, though, is determine the total parallel and angular misalignment in the vertical plane. We'll use information from the data sheet to find the answers. This data sheet is designed to help make the calculations easier. We'll start with the parallel misalignment. The dial indicator reading here is minus 17 mils. If we follow over from the box, we see that we must first divide the reading by 2. That gives us an answer of minus 8.5 mils. Next, we have to subtract the amount of bar sag from this answer. That leaves us with minus 6.5 mils. This value gets written in the box labeled PV and represents the parallel misalignment in the vertical plane. Now, we need to determine the angular misalignment in the vertical plane. Since the A dial indicator reading represents angular misalignment and bar sag isn't a factor for A dial indicator readings, all we have to do is transfer the reading to the box labeled AV. With this information, we can create a graph to determine the move. One nice thing about graphs is that you can see the correction that's needed. To create the graph, you'll need a piece of graph paper. Now we'll need a point of reference, which we'll call the base point. It should be located on the far left side of the graph. Next, we'll draw a straight line from the base point to the right side of the graph. We'll call this line the baseline. Now, the horizontal graduations on the graph will represent increments of 1 inch. The vertical graduations will represent increments of 1 mil, or 1/1000th of an inch. We're going to need some of the information from the data sheet to finish the graph. First, we'll need the value of D, which is the swing diameter of the A dial indicator stem. In this example, D is 10 inches. To plot D on the graph, we'll start at the base point and move along the baseline the value of D. In this case, we move 10 increments. We'll make a point here. This point will be labeled D. Now we'll need the value of X, which is the distance between the target of the A dial indicator and the center line of the support bolt for the inboard motor foot. In this case, X is 12 inches. To plot this point, we'll move along the baseline from point D 12 increments, and we'll make a point here that will be labeled X. Next, we need the value of Y, which is 24 inches in this example. If you recall, Y is the distance between the target of the A dial indicator and the center line of the support bolt for the outboard motor foot. We'll move from point D along the baseline 24 increments and make a point labeled Y. The next value we'll need from the data sheet is the value of AV. In this case, the value is plus 6 mils. To plot point AV on the graph, we must start at the base point. Now, if AV is a positive value, we move up from the base point the value of AV. If AV is negative, we move down from the base point the value of AV. Since AV is positive in this example, we'll move up 6 increments and place a point labeled AV. Now, starting at point AV, we'll draw a straight line that intersects point D. At this point, the graph shows us the relationship between the angular misalignment in the vertical plane and the desired alignment of the shafts. This line, which we'll call the reference line, represents the angular misalignment in the vertical plane. The baseline, then, represents the position the movable component must be moved to in order to eliminate angular misalignment. What we need to do now is factor in the parallel misalignment that's present. Starting at point X on the baseline, we'll follow straight down to the reference line and make a point. This point is labeled XA. Now we'll do the same thing with point Y on the baseline. We'll follow straight down to the reference line and make a point. This point will be labeled YA. Now we need to add the information for parallel misalignment in the vertical plane. To do that, we'll need the value of PV from the data sheet. In this example, PV has a value of minus 6.5 mils. To plot this information on the graph, we need to start at point XA. Now, if the value of PV is positive, we move up from point XA the value of PV. However, in this case, PV has a negative value, so we'll have to move down from the point XA the value of PV, which is 6.5 mils. We'll make a point here labeled XAP. Now we'll do the same thing at point YA. We'll move down the value of PV, which is 6.5 mils, and make a point labeled YAP. Next, we'll draw a dashed line that intersects both points XAP and YAP. This line, then, represents the combined angular and parallel misalignment in the vertical plane. To determine the amount the motor needs to be moved in order to bring the shafts into alignment in the vertical plane, we'll need to do a couple of things. The first thing we need to do is check whether the dashed line is above or below the baseline. If it's below the baseline, as it is here, we have to move the motor up. That means adding shims under the motor feet. If the dashed line were above the baseline, we would have to lower the motor. That would involve removing shims from the motor feet. The second thing we need to do is count the increments between points X and XAP and between points Y and YAP. In this example, the distance between point X and point XAP is greater than 13.5 mils, but less than 14 mils. Because you generally won't be dealing with shims less than 1 mil, it's acceptable to round these values. So in this case, we can round off the value to 14 mils. If we count the increments between point Y and point YAP, we find that the distance is greater than 20.5 mils, but less than 21 mils. So we can round this value to 21 mils. So in this example, raising the inboard feet 14 mils and the outboard feet 21 mils will correct for both angular and parallel misalignment in the vertical plane. Well, we've seen how a graph can be plotted and used to determine how to correct for misalignment in the vertical plane. Now let's take some time to discuss how the actual move is made. Correcting for misalignment in the vertical plane involves adding or removing shims under the feet of the movable component. The graph we just prepared indicates that to correct for the vertical misalignment, we'll have to add 14 mils to the inboard feet and add 21 mils to the outboard feet. One thing you'll need to remember about shims is that as the number of shims increases, it becomes more likely that the shim pack may flex or shift. If that occurs, the shafts may become misaligned when the equipment is operated. For that reason, it's generally recommended that shim packs be limited to no more than 3 or 4 shims. Once the proper sized shim packs are obtained, the support bolts can be loosened and the shim packs installed. You'll notice that the mechanic is using a pry bar to raise each foot enough to insert the shim pack. If the movable component had been bigger, hydraulic jacks might have been needed to lift the foot high enough. Once all of the shim packs are in place, the mechanic retightens the support bolts. In this part of the program, we've discussed how to use a graph to determine the amount of movement needed to correct for misalignment in the vertical plane and how the actual move is made. In the next part of the program, we'll look at how misalignment in the horizontal plane is measured, graphed, and corrected using the rim and face method. Up to this point, we've seen what's involved in using the rim and face method to measure, graph, and correct for misalignment in the vertical plane. In this part of the program, we're going to do the same thing for the horizontal plane. So let's get started. Since we're dealing with the horizontal plane, we'll first have to rotate both shafts so that the brackets are at the 3 o'clock position. And like before, we'll use the marks on the pump to make sure we're at the exact position. Next, the face of each dial indicator is rotated so that a reading of 0 is obtained. Then, the shafts are rotated a full 360 degrees back to the 3 o'clock position to make sure the brackets and dial indicators are securely fastened. Both indicators read 0, so everything seems to be in order. Now, while watching the indicators, the shafts are rotated to the 9 o'clock position, and readings are taken on both dial indicators. In this position, the P dial indicator reads +8 mils, and the A dial indicator reads -5 mils. We'll record these values on the data sheet. As you can see, there is another set of boxes for the horizontal plane readings. The P dial indicator reading gets written down here next to the circle labeled P. The A dial indicator reading is recorded here next to the circle labeled A. Like before, zeros are entered into the boxes at the 3 o'clock position because we set the dial indicators to 0 at that position. When measuring misalignment in the horizontal plane, bar sag isn't a factor, so we'll only have to divide the P reading by 2 to determine the parallel misalignment in the horizontal plane. The answer gets written in the box labeled PH. And like before, the A dial indicator reading represents the angular misalignment, so its value gets transferred to the box labeled AH. Now we have to take another set of readings to make sure that our initial readings were accurate. We get the same readings this time as well, so everything still looks good. The next thing we have to do is prepare the graph. Basically, it's the same as the one we saw earlier, only this time we'll be graphing horizontal instead of vertical misalignment. We start by plotting the base point, then draw in the baseline. And we'll need the values of D, X, and Y just as before. Now we'll plot these values on the baseline. D has a value of 10 inches, so starting at the base point, we move over 10 increments and place a point labeled D. X has a value of 12 inches, so we start at point D and count over 12 increments and make a point labeled X. Then we do the same thing with Y, which has a value of 24 inches. We move over 24 increments from point D and place a point labeled Y. Since we're graphing misalignment in the horizontal plane, we'll need the value of AH next. In this example, AH has a value of -5 mils. To plot point AH on the graph, we start at the base point. If AH is a positive value, we move up from the base point the value of AH. But since AH has a value of -5 mils in this example, we'll have to move down from the base point 5 increments and make a point labeled AH. Next, we need to establish the reference line. To do that, we draw a straight line from point AH that intersects point D. Now, starting at point X on the baseline, we move straight up to the reference line and make a point labeled XA. And we do the same thing from point Y on the baseline. We'll move straight up to the reference line and make a point labeled YA. Next, we need the value of pH from the data sheet. In this example, it has a value of +4 mils. Starting at point XA, we'll have to move up or down to plot the parallel misalignment information. Like before, if pH has a negative value, we move down from point XA. In this example, pH has a value of +4 mils, so we'll move up from point XA 4 increments and place a point labeled XAP. Now we'll do the same thing from point YA. We'll move up 4 increments and make a point labeled YAP. Then we'll draw in a dashed line that intersects points XAP and YAP. This line represents the combined angular and parallel misalignment in the horizontal plane. The baseline represents the position we'll have to move the movable component to in order to bring the shafts into alignment. To determine how much to move the motor in order to bring the shafts into horizontal alignment, simply count the increments between points X and XAP and between points Y and YAP. One thing to remember here is how to determine which direction to move the motor. When graphing misalignment in the horizontal plane, if the dashed line is above the baseline, as it is here, you move the motor towards 9 o'clock. If the dashed line is below the baseline, you move the motor towards the 3 o'clock position. At this point, the motor can be moved to correct for misalignment in the horizontal plane. Let's see how this is done. In order to correct for misalignment in the horizontal plane, the mechanic is mounting dial indicators on both an inboard foot and an outboard foot. This will enable him to determine when the proper amount of movement has been made. Once the dial indicators are securely mounted, each one is adjusted for the amount of movement that is required. In this case, the inboard dial indicator is set to 10 mils, and the outboard dial indicator is set to 16 mils. Then the support bolts are loosened. Once the movable component is loose, the mechanic begins making the move. In this example, he's using jacking bolts to move the motor. At the same time, he's watching the dial indicators. When the dial indicators read 0, the move has been completed. Now, the mechanic is retightening each support bolt. As he tightens each bolt, he's checking the dial indicators to make sure that the motor doesn't shift. Once all of the support bolts have been properly tightened, the shafts of both components should be aligned properly. However, the mechanic will take another set of dial indicator readings to verify that the alignment is within tolerances specified for the equipment. Data sheets usually have a place for the final set of readings to be recorded. According to these final readings, the alignment is within specs, so the equipment can be returned to service. It's important to note that because of thermal growth and other factors, the final set of readings you take won't necessarily be 0, but the final readings should indicate that the alignment is within the specified tolerance. By now, you should have a general understanding of alignment theory, what's involved in preparing for an alignment, and how to use the rim and face method to accurately align shafts. If you take the time to fully understand what's been covered in this program and practice the techniques we've discussed, you'll be doing a big part in keeping your facility's rotating equipment running smoothly and efficiently.